Greetings, traveller. It is so wonderful to have you join us in the archives yet again. Tonight you are entering a medieval town that survives, not because of abundance, but because of careful and strategic planning. Beneath the streets, markets, and stone buildings above you, entire food systems operate out of sight. Grain is measured and rotated, meat is salted and sealed. Nothing in this town is done accidentally, and very little is comfortable. Tonight we shall explore how medieval citizens stored food beneath their cities and towns, how those underground systems were built, maintained, regulated, and stretched across seasons, shortages, and sieges. But first of all, tell us where in the world you are watching this video from. It is always so interesting to learn just how far our boring, sleep-inducing history goes. This is not a story about meals. No, this is a story about systems. So settle in, slow your breathing, and follow the process carefully. The town above depends on what you are about to see below. You are standing in a medieval town, above ground, where nothing about daily life suggests abundance. Streets are narrow, storage space is limited, buildings are timber-framed, packed close together and constantly at risk of fire, rot, theft, and spoilage. Above-ground medieval towns were structurally hostile to long-term food storage. In the medieval period, towns did not store food underground because it was clever or innovative. They did it because most other options failed. Food preservation faced 5 persistent enemies: moisture, heat, air, pests, and human interference. Medieval technology could not eliminate these forces. It could only manage them by choosing the least hostile environment available. Beneath towns and cities, underground spaces provided the closest approximation of stable conditions that medieval builders could achieve without mechanical systems. Below ground, temperature fluctuated far less across seasons. Soil and stone absorbed summer heat and released it slowly in winter. In most regions of Europe, underground temperatures remained cool but above freezing, often between 8 and 13 degrees Celsius, depending on depth and geology. This slowed microbial growth, insect activity, and chemical degradation of stored foods. Cool temperatures alone extended the life of grains, legumes, root vegetables, and preserved meats by months. Humidity was more difficult. Underground spaces could trap moisture, encouraging mold and rot. Medieval builders responded by choosing specific locations for storage. Cellars and storage chambers were dug into well-draining soils, when possible, such as gravel or compacted sand. In wetter regions, storage rooms were lined with stone and lime mortar to regulate moisture. Ventilation shafts were cut to allow slow air exchange without drafts. Floors were sometimes raised on stone plinths or wooden slats to keep sacks and barrels from direct ground contact. The underground also offered protection. Food was wealth. Grain shortages caused riots, political instability, and population collapse. Storing food beneath guarded town centers reduced theft, limited access, and placed reserves under civic control. Many medieval towns prohibited large private grain hoards above ground. Instead, they centralized storage in communal granaries, vaults, and cellars controlled by municipal authorities, guilds, or ecclesiastical institutions. You see stairs descending beneath streets, marketplaces, and administrative buildings. These were not private cellars for household convenience. They were components of urban survival systems. Underground storage also reduced fire risk. Medieval towns burned frequently. Fires destroyed homes, workshops, and warehouses. Subterranean stores, especially those vaulted in stone, often survived fires intact. Town records from the late medieval period repeatedly note that grain stores below ground were among the few assets remaining after major fires. This system had limits. Underground storage did not create abundance. It delayed scarcity. It transformed unpredictable harvest cycles into manageable logistical problems. Food stored below towns bought time. Time for trade to resume. Time for new harvests. Time for authorities to ration supplies. The underground was not invisible to medieval people. It was understood, regulated, taxed, inspected, and feared. Spoiled grain meant famine. Flooded cellars meant catastrophe. Every decision about depth, location, container, and access carried long-term consequences. You are not looking at a single system. You are standing above layers of overlapping solutions, developed slowly, enforced unevenly, and constantly maintained to keep entire populations alive through winters, droughts, sieges, and political failures. You move downward into the spaces where medieval food storage actually occurred. These were not improvised holes beneath houses. They were engineered environments shaped by geology, labor constraints, and administrative priorities. The simplest form was the domestic cellar. These were shallow excavations beneath homes, typically 1 to 2 meters below ground level. Domestic cellars stored small quantities of food intended for household use. Root vegetables such as turnips, onions, carrots, and parsnips were kept in bins layered with sand or straw. Salted meat and cheese were stored in hanging racks or wooden shelves to limit contact with moisture. Grain was rarely stored long-term in private cellars due to spoilage risk and municipal restrictions. More critical were communal storage structures. Town granaries were often partially or fully subterranean. Some were built as sunken stone halls with vaulted ceilings, accessed by narrow stairways and secured with heavy doors. Others were above-ground buildings with deep storage basements extending below frost level. Depth was calculated carefully. Too shallow and temperatures fluctuated. Too deep and groundwater intrusion became likely. In flood-prone towns, storage chambers were raised slightly above the lowest groundwater table and surrounded by drainage trenches filled with gravel. In regions with high water tables, underground storage was limited or avoided entirely in favor of elevated granaries. Walls were thick, usually stone or brick bonded with lime mortar. Lime was mildly antiseptic and discouraged some mold growth. Ceilings were vaulted to distribute pressure and prevent collapse. Flat timber ceilings were avoided in large storage chambers because they attracted pests and trapped moisture. Ventilation was critical and minimal. Small air shafts, sometimes disguised as street features above ground, allowed slow air circulation. The goal was not fresh air, but stale stability. Too much airflow dried grain excessively or encouraged insect movement. Too little allowed condensation. Floors were usually stone or packed earth treated with lime. Wooden floors were rare due to rot and infestation. In some regions, floors were sloped slightly toward drainage channels to direct moisture away from stored goods. Access points were deliberately inconvenient. Narrow staircases limited traffic. Heavy doors slowed entry. Some granaries required multiple keys held by different officials to prevent theft or corruption. This was an early form of institutional control over food reserves. The lighting was minimal. Oil lamps and torches were used sparingly due to fire risk. Inspections were conducted quickly and methodically. Darkness reduced insect activity and prevented drying of exposed surfaces. Maintenance was constant. Storage chambers were emptied, cleaned, aired, and repaired on a strict schedule. Lime washing was repeated annually. Wooden containers were replaced or repaired regularly. Any sign of infestation triggered immediate action, often involving removal and destruction of affected stores. You see that these spaces were not passive containers. They were active systems requiring labor, oversight, and constant decision-making. A neglected cellar failed quickly. A well-managed one extended the life of stored food far beyond what surface storage allowed. These architectural choices were not universal. They varied by region, climate, soil type, and political organization. But across medieval Europe, the principle remained consistent. Food survived longest, where human interference was controlled and environmental conditions changed as little as possible. Underground storage was not a single innovation. It was a discipline. You are now looking at the most critical element of medieval food storage beneath towns. Grain, wheat, rye, barley, oats, and spelt form the caloric backbone of medieval urban life. Almost every other stored food supported grain consumption rather than replacing it. Underground storage systems were designed first and foremost around grain preservation. Grain was uniquely suited to long-term storage, but only under strict conditions. Once harvested, grain remained biologically active. Moisture triggered germination. Heat encouraged mold. Oxygen enabled insects. Medieval storage systems attempted to slow all three without fully eliminating them, because full elimination was technologically impossible. Before grain ever reached underground storage, it underwent multiple preparatory stages. Grain was dried in the open air after harvest, often on threshing floors or elevated platforms. Moisture content was reduced as much as possible before transport. Wet grain was dangerous. Town ordinances frequently rejected grain deliveries during damp weather or required additional drying periods before acceptance into civic stores. Once dried, the grain was cleaned. Chaff, dust, broken kernels, and insect larvae were removed through sieving and winnowing. This reduced spoilage risk and extended storage life. Grain entered underground storage only after passing inspection. Municipal officials or guild-appointed inspectors were responsible for certifying quality. Inside subterranean spaces, grain was stored in three primary forms: loose bulk storage, sacks, and barrels. Bulk storage involved piling grain directly into stone bins or wooden compartments. This method reduced container costs but increased spoilage risk if moisture penetrated the pile. Sacked grain was easier to rotate and inspect, but required constant monitoring for rodent damage. Barrels provided the best protection, but were expensive and labor-intensive to maintain. Grain depth mattered. Piles were kept shallow enough to prevent internal heat buildup. Deep piles trapped moisture and encouraged fermentation. Medieval storage manuals and town records indicate that grain was turned periodically. Workers used shovels and rakes to redistribute grain, breaking up clumps and exposing damp pockets. This labor was slow, monotonous, and essential. Insect infestation was inevitable. Weevils, beetles, and moth larvae entered storage despite precautions. Underground conditions slowed their life cycles but did not stop them. Towns responded with regular inspections, fumigation using smoke or herbs, and physical removal of contaminated grain. Heavily infested stores were sometimes discarded entirely, a loss that could destabilize food supply. Rotation was a central principle. Grain was rarely stored for more than 1 or 2 years. Older stock was distributed first, often sold at controlled prices during shortages. New harvests replenished reserves. This rotation required careful record-keeping. Tallies, ledgers, and physical markers tracked quantities, origins, and age. Grain beneath towns was not static wealth. It was a managed reserve, constantly adjusted to balance preservation against consumption. Failures occurred when rotation slowed, inspections lapsed, or moisture penetrated storage chambers. In such cases, spoilage cascaded quickly. You are seeing a system that depended on attention rather than innovation. Grain storage worked not because medieval people mastered biology, but because they respected its limits. You now move beyond grain to the secondary layers of underground food storage. These foods did not replace bread, they supplemented it. Their role was to provide protein, fats, and dietary stability when fresh supplies disappeared. Salt was the foundation of non-grain preservation. Meat and fish were preserved through salting, drying, smoking, or combinations of all three. Underground storage chambers housed salted beef, pork, and fish, packed into barrels. Salt drew moisture from flesh, inhibiting bacterial growth. However, salt-preserved foods remained vulnerable to spoilage if barrels leaked or humidity rose. Barrels were inspected frequently, salt levels were monitored, brine was replenished as needed. If brine became diluted, spoilage accelerated. Town regulations often specified barrel construction standards and imposed fines for faulty containers. Leakage underground was a serious hazard as saltwater damaged stone floors and encouraged rot. Fish storage was particularly important in towns subject to religious fasting rules. Salted herring, cod, and other preserved fish were stored in large quantities beneath urban centres. These stores were often controlled by merchant guilds rather than municipal authorities, creating parallel storage systems within the same underground spaces. Cheese formed another critical reserve. Hard cheeses aged well in cool, stable environments. Underground cellars provided ideal conditions. Cheeses were turned regularly, inspected for mold, and cleaned. Spoiled wheels were removed quickly to prevent contamination. Cheese storage required skilled labor and constant attention. Root vegetables were stored differently. Turnips, carrots, parsnips, and beets were stored in pits or bins layered with sand, straw, or soil. Underground temperatures prevented freezing while limiting sprouting. These stores were more fragile than grain or salted meat. Excess moisture caused rot. Dry conditions caused desiccation. Loss rates were high, and root vegetables were considered short to medium-term reserves. Dried legumes such as peas and beans were stored similarly to grain but in smaller quantities. They were vulnerable to insects and moisture but provided essential protein. Their storage life was shorter, requiring careful rotation. Underground storage also included fats. Rendered animal fats and oils were kept in sealed containers. These were highly sensitive to temperature and air exposure. Rancidity was common. Fats were often stored in the coolest available spaces and used relatively quickly. Each category of food imposed different architectural and maintenance requirements. Medieval underground storage systems were therefore compartmentalized. Grain was separated from meat. Root vegetables were isolated from dry stores. Smell, moisture, and contamination risks dictated layout. You are seeing a layered system designed not for efficiency but for survival. Each preserved food type bought time under specific conditions. Together, they formed a fragile buffer against hunger. When any one component failed, pressure increased on the others. Underground storage was not redundant, it was interdependent. You are now watching the storage system change with the calendar. Medieval underground food storage did not operate at a constant state. It expanded, contracted, and shifted purpose according to the agricultural year. Seasonality governed everything, from labor allocation to inspection schedules. Late summer and early autumn were the most intense periods. Harvests arrived in large volumes over a short window. Grain deliveries surged, root vegetables were pulled from fields, livestock was slaughtered before winter feed shortages. Underground storage spaces filled rapidly, often to capacity. During this period, errors were most likely. Wet grain entered stores. Inadequate drying led to mold. Overfilled chambers reduced airflow. Town authorities attempted to manage this surge by staggering intake. Harvests were sometimes stored temporarily above ground, under watch, until conditions allowed proper underground placement. Storage rules were relaxed and tightened seasonally. Inspectors worked longer hours. Laborers rotated grain continuously to dissipate residual heat from harvest. Winter marked the longest static phase. Underground stores were at their fullest, and fresh food availability declined. Consumption rates increased as markets depended more heavily on reserves. Cold surface temperatures reduced insect activity but increased condensation risks underground. Ventilation was adjusted carefully. Excess airflow introduced cold, encouraging freezing and cracking of containers. Insufficient airflow caused moisture buildup. Spring introduced instability. Temperatures fluctuated rapidly. Grain began to sweat as external warmth penetrated underground spaces. Mold outbreaks were common. Root vegetables sprouted or softened. Cheese aged too quickly. Storage managers responded by accelerating distribution. Older stock was released first. Towns sometimes reduced rations slightly to avoid sudden losses later. Summer was a depletion phase. Underground stores emptied steadily. Inspection frequency increased again, not to protect abundance, but to prevent sudden collapse. Empty chambers were cleaned, dried, and repaired in preparation for the next harvest. Lime washing occurred during this period to reset storage environments. Seasonal cycles shaped architectural decisions. Storage chambers were designed to tolerate worst-case seasonal conditions rather than ideal ones. Drainage systems anticipated spring melt. Ventilation shafts were positioned to avoid direct summer heat. Access points were reinforced against winter ice. You see that underground storage was never static. It functioned as a living system synchronized to agricultural rhythms. Failure to respect seasonality produced cascading problems. Successful towns understood that preservation was not a single act, but a continuous process tied to the calendar. You now observe the human systems that kept underground storage functional. These spaces did not preserve food on their own. Labor and oversight determined success or failure. Maintenance labor was unglamorous and constant. Workers cleaned floors, repaired stonework, replaced rotting timbers, and removed debris. Grain turning required physical endurance and precision. Too aggressive and kernels cracked. Too gentle and moisture pockets remained. This work followed strict routines developed through experience rather than theory. Inspection roles were formalized in many towns. Officials were appointed to oversee grain quality, container integrity, and storage conditions. These roles were often rotated to limit corruption. Records were kept using tallies, marks, and written accounts. Errors in accounting translated directly into shortages or unrest. Pest control was continuous. Traps were set for rodents. Cats were maintained in storage facilities. Structural gaps were sealed with stone or metal. Infestations were expected and managed rather than eliminated. Complete control was impossible. Labor discipline mattered. Unauthorized access to storage spaces was restricted. Keys were controlled. Some facilities required multiple officials present for entry. This slowed work but reduced theft. Workers were supervised closely during handling of high-value stores, such as grain and salt. Storage maintenance competed with other urban labor demands. During crises, maintenance was often deferred, increasing long-term risk. Successful towns resisted this temptation. Records show that towns that preserved maintenance schedules recovered more quickly from famines and sieges than those that neglected them. You notice that storage systems reflect governance quality. Well-managed towns treated underground storage as civic infrastructure. Poorly managed towns treated it as emergency insurance. The difference determined survival outcomes. The underground was not hidden labour, it was simply undervalued labour. Its success was measured in absence. No riots, no shortages, no sudden collapses. Maintenance was the quiet cost of stability. You are now examining where medieval underground food storage failed. These systems did not collapse randomly. They failed at predictable points when constraints were ignored, maintenance was deferred, or environmental conditions exceeded design limits. Water was the most dangerous threat. Flooding entered storage spaces through rising groundwater, broken drainage channels, or structural cracks. Even minor water intrusion ruined grain rapidly. Once wet, grain fermented, heated internally, and spread spoilage to surrounding stores. Town records repeatedly describe emergency grain removals following cellar flooding, often too late to prevent losses. Structural failure followed neglect. Stone walls cracked under soil pressure. Vaults weakened when mortar degraded. Wooden supports rotted in damp environments. Collapses buried stored food and made recovery impossible. Repairs were expensive and disruptive. Some towns abandoned compromised storage chambers permanently, reducing total capacity for decades. Ventilation failures were more subtle but equally damaging. Blocked air shafts caused condensation buildup. Excess ventilation dried grain excessively or introduced temperature shocks. Balancing airflow required constant adjustment. Inexperienced oversight often produced well-intentioned but harmful changes. Infestation outbreaks escalated quickly. Insects multiplied faster than inspection cycles could respond. Rodents accessed storage through small breaches. Once established, infestation spread between chambers. Towns sometimes isolated affected sections, sacrificing stored food to protect remaining reserves. Administrative failure amplified physical risks. Corruption diverted food reserves. Poor record-keeping hid shortages until markets reacted violently. Delayed rotation caused spoilage. Political instability often preceded storage collapse rather than resulting from it. External shocks exposed vulnerabilities. Sieges blocked resupply. Trade disruptions delayed replacement stocks. Consecutive poor harvests overwhelmed storage capacity. Underground systems were buffers, not solutions. They extended survival windows but could not sustain populations indefinitely. You see that failure was rarely singular. Multiple small weaknesses compounded into catastrophic loss. Medieval towns that survived repeated crises did so by identifying and reinforcing known failure points rather than seeking perfect security. You're now observing underground food storage under maximum stress. Sieges, blockades, and political unrest transformed routine systems into survival mechanisms. During sieges, access to storage was tightened, rationing protocols were activated, consumption rates were recalculated daily. Grain distribution shifted from market-based access to controlled issuance. Underground stores became strategic assets guarded by armed personnel. Ventilation was adjusted to minimize detection. Smoke and heat signatures above ground could reveal storage activity. Lighting underground was reduced further. Movement was restricted to essential personnel. Maintenance continued under pressure, often with reduced labor. Rotation rules changed. Older stock was consumed first, but quality thresholds dropped. Marginal grain was mixed with better stores. Spoilage tolerances increased. Nutritional quality declined, but caloric continuity was prioritized. Salted meat and fish became primary protein sources. Root vegetables were consumed early due to spoilage risk. Cheese provided sustained calories but required careful rationing. Fats were used sparingly due to limited supply. Siege conditions revealed system limits. Once underground stores fell below critical thresholds, towns faced collapse. Records describe sudden starvation after long periods of apparent stability. Underground storage delayed the crisis but compressed its final stages. After sieges ended, recovery depended on remaining storage integrity. Towns with preserved infrastructure rebuilt faster. Those with destroyed underground systems faced prolonged shortages even after trade resumed. You see that underground storage shaped medieval warfare outcomes indirectly. It determined how long towns resisted, how populations endured, and how quickly recovery occurred. Storage was not passive background infrastructure. It was an active factor in political and military history. You are now observing the long-term effects of maintaining food beneath medieval towns over generations. These systems shaped urban development, social hierarchy, and economic behavior in ways that extended far beyond preservation itself. Underground storage influenced city planning. Streets, marketplaces, and administrative buildings were often constructed above existing storage spaces. Once established, underground chambers constrained later construction. New foundations had to accommodate old vaults. Drainage systems were rerouted. In some towns, entire districts developed around protected storage zones. Food reserves affected population stability. Towns with reliable underground storage experienced fewer sudden population collapses during poor harvest cycles. This stability encouraged migration from rural areas. As urban populations grew, demand for storage increased, leading to deeper excavations and expanded facilities. This feedback loop intensified dependence on underground systems. Economic behavior adjusted accordingly. Grain prices were influenced not only by harvest yields but by storage capacity. Towns with larger reserves could delay market release, stabilizing prices. Those with limited storage experienced sharper price volatility. Underground storage thus became an economic regulator, whether intentionally or not. Social consequences followed. Control over storage meant control over survival. Municipal authorities, guilds, and religious institutions that managed underground stores accumulated political power. Access decisions during shortages shaped public trust and resentment. Storage administrators became targets during crises, regardless of fault. Labor specialization increased. Storage maintenance, inspection, and accounting evolved into distinct roles. Knowledge accumulated over generations. Mistakes became institutional lessons. Towns with continuity in management performed better than those with frequent administrative turnover. There were also hidden costs. Underground storage tied towns to constant maintenance obligations. Deferred repairs accumulated silently. When failures occurred, recovery was slow. Abandoned storage spaces became hazards. Collapses undermined streets and buildings above. In some cases, old storage chambers were sealed permanently, reducing usable capacity. Environmental consequences emerged. Salt runoff damaged masonry and soil. Drainage alterations affected groundwater patterns. Repeated excavation weakened structural integrity in some districts. Medieval towns traded long-term geological stability for short-term survival capacity. You see that underground food storage was not a neutral adaptation. It reshaped towns physically, politically, and economically. It created resilience at the cost of complexity. Once adopted, it could not be abandoned without consequence. You are now standing at the end of the system, observing why medieval towns continued to rely on underground food storage despite its risks and limitations. The system persisted because it worked better than alternatives available at the time. Above-ground storage failed too easily. Transport networks were unreliable. Agricultural output fluctuated unpredictably. Underground storage offered the most controllable environment medieval technology could provide. It also aligned with medieval constraints. It required labor rather than advanced tools. It relied on stone, earth, and wood rather than precision engineering. It scaled incrementally. Towns could expand storage gradually as populations grew. This adaptability ensured longevity. The system reveals medieval priorities. Preservation was not about comfort or abundance, it was about delaying disaster. Underground storage did not eliminate hunger, it managed hunger. It turned existential threats into administrative problems, at least temporarily. You observe that success depended less on architecture than on discipline. Towns that respected maintenance schedules, rotation rules, and inspection protocols survived longer. Those that ignored them collapsed faster. Technology mattered less than governance. Underground storage also reveals a pragmatic worldview. Medieval towns accepted loss as inevitable. Spoilage was expected, infestation was managed, not eliminated. The goal was not perfection, it was survival through imperfect means. As you look upward from beneath the town, you see streets continuing above, unaware of the system sustaining them. This separation was intentional. Food security worked best when invisible. Panic followed visibility. The underground was not a secret, it was simply out of sight. Medieval towns survived as long as they did because they invested labor, attention, and authority into spaces that few people saw and fewer appreciated. Beneath the stone and timber, these systems quietly absorbed failure, delayed catastrophe, and bought time. Time was the most valuable resource they stored. You are now leaving the underground, traveler. Above you, medieval streets continue as they always did, largely unaware of the grain turned, the barrels inspected, and the quiet labor that kept famine delayed rather than avoided. These food systems were never perfect. They were simply disciplined, maintained, and respected long enough to matter. If you enjoyed this deep dive into medieval food storage systems and the infrastructure beneath the town, you are invited to like this video, subscribe to the channel, and ring the bell so you can find your way back into the archives when the next record is opened. New travelers arrive quietly here. Returning travelers know where to listen. Until next time, rest well, and remember, the most important systems are usually the ones you never see. Sleep well, traveler.